So now that we know a little bit about what the derivative actually is, what we want to do is try and find some shortcuts. We'll maybe take a look at some more limits where we do the derivative using that limit definition that we learned the last video or whenever that was. But what we want to do is see if we can generalize some of these and learn how to deal with specific functions and function types. First, before we do that, though, let's just talk about some notation. This is the one that we see a lot in this kind of a class. We'll be given a function f of x, and you'll have to find f prime of x. And we know that that prime notation represents the fact that we're looking at a derivative there. Similarly, sometimes we can just define a function instead as y, and then we'll be able to use y prime. This dy over dx also means the derivative of y. Maybe I'll put that in there. This is the derivative of y specifically. And this is meant to kind of call back to the fact that this kind of looks like delta y over delta x, which is really our formula for slope, change in y over change in x. Our deltas become d's. We call these things differentials here, and it mostly represents the idea that we're looking at these changes in y and changes in x, but they're infinitely small because we have that limit as h goes to 0 and all that kind of stuff. And this is a similar thing. This one just means literally the derivative of f of x. So a lot of times you'll see some function written in here and we'll put d over dx in front of it, and this d over dx literally means the derivative of whatever comes next. When we put the variable name up in top, this means the derivative of y specifically. We have to have y defined, but these all basically mean the same thing. So let's get into some properties now. First, we'll take a look at some constant functions. I think if you've got a little chart handout or something like that from Canvas, you can start filling these in as we go. But when we talk about constant functions, we're going to be talking about functions like f of x equals 7. Specifically, to figure these things out, we could take a look at the limit definition for this. We could say f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. But realistically, we'll just kind of think about this stuff graphically when we talk about these constant functions. So here we'll call our function k, where k is a constant. And what I want to do is just pick an example. I'll do my examples in blue for this. And let's just pick that function that we had earlier, 7. And what I want to do is draw a picture of what this is. So if this is our graph, we'll call the red our actual function. Constant functions just look like horizontal lines, like this. So this would be our function, f of x equals 7. And if we're trying to figure out the derivative, what we're really trying to figure out is what the slope of this thing is. Specifically, the slope at any point with some x value. We can move that point anywhere, but we want to find the instantaneous slope here, or the slope of a tangent line or something like that. What you're going to notice is that the slope here is 0 everywhere. So constant functions are actually pretty easy. For any constant, the derivative is 0. So if we could say if f of x equals 7, then we know that f prime of x is 0 everywhere because the slope on this red line is always 0. So any constants, the derivative is going to be 0. These are pretty easy ones. Let's build this up now, and we'll think about power functions. We're only going to look at ones with, well, no, I won't give anything away. We'll just think of some basic power functions like x squared, x cubed, and x to the 4. What I would encourage you to do is use the limit definition for each of these. I'll write it out. That's our derivative of x squared. The derivative of x cubed is going to be really similar. It's just going to be x plus h cubed minus x cubed over h. And finally, for x to the 4, it's the same thing, except it's x plus h to the 4 minus x to the 4 over h. For all of these, what we're going to want to focus on is multiplying these out. They're a little annoying, especially this x plus h to the 4, because it's literally x plus h times x plus h times x plus h times x plus h. There's a lot of distributive property to do here. Take a couple minutes, pause the video, try and multiply all these things out, and then you'll notice that for all of these, it's not going to be terribly hard to figure out what's going on after that. The multiplication will be the hard part. After that, you'll subtract the x squared stuff and see what happens. And see if you can come up with a pattern. I'll wait. Okay, so if you've done that, maybe I'll go back here. If you've done that, this is my universal symbol for you need more work. We'll find that the derivative here is 2x. And with this one, we'll find that the derivative is 3x squared. And with this one, that's supposed to be a dot, dot, dot. We'll find that the derivative is 4x cubed if you do all that stuff. So we can get a pretty good pattern here. Generally, we have the coefficient being whatever our exponent was, n, and then our new exponent is just one less. So the general rule for any power function, x to the n, is that the derivative is n, x to the n minus 1. The way that it works really is this. You maybe have seen this before. This is called Pascal's triangle. If you haven't seen this, it's not terribly difficult. It's basically just a pattern of numbers. Each row of our triangle starts and ends with 1, and then the next values are all just sums of the two numbers above it. So this one will be 5. Here we'll say 4 plus 6 is 10, and then we'll have 10 here because 6 plus 4. 4 plus 1 is 5, and 1. All blah, 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 blah. The reason that we care about that is that these are the coefficients on all of these red underlined things that we multiplied out. X plus h squared is x squared plus 2xh plus h squared. X plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed, and so on and so forth. And so we can use Pascal's triangle to notice a pattern each time. We're going to multiply these things out, but then if you remember, if I go back, in each of these, we end up subtracting off that first term. So on each of these things, these first pieces end up going away. And then on each of the examples that you had, you could factor out a common factor of h and divide, and you were left with just this term here. So this Pascal's triangle basically shows us that these are the terms that are going to be left out after we factor our h's out, cancel things, and then make h go to 0. You're going to be left with 2x, 3x squared, 4x cubed, 5x to the 4, etc., etc., etc. This isn't a formal proof for it. If you want to see a formal proof, you can look in the text. I'm sure there's one in there. It uses the binomial theorem, which basically is a theorem that tells you how to multiply two things by itself a bunch of times. That's really all this is based on. So what we can do now, maybe I'll just erase some of this stuff so I can write a nice little example, is we can take a look at a whole bunch of examples and they become really easy. Let's say y is x to the 7. We don't even have to think about it now. We can say y prime is 7x to the 6. If we have f of x being x to the 19, then instead of having to multiply everything and do that limit, we can just say that the derivative is going to be 19x to the 18. Bring this exponent out front, subtract 1 from the exponent, and you're good to go. So the power rule is really nice for when we're dealing with these power functions. We want to take a look at the reciprocal function. This is one that we've already done. We already did the limit as h went to 0 of 1 over x plus h minus 1 over x over h, which, if you remember, was the derivative of the reciprocal function. The reciprocal function is f of x equals 1 over x. We already did all of this work, and we found out that the derivative was negative 1x squared. You can go back in your notes and take a look at that. If you remember, the key was combining these two things using common denominators. So I've already gone ahead and written that rule up there. Excuse me. Well, one of the things that I want to show off is that we can actually take this and rewrite it. We can say this is the same thing as using a negative exponent, x to the negative 1. And if we have this, we can do the power rule and say bring the negative exponent out front, negative 1x, and then our new exponent is our old one minus 1. So we have negative x to the negative 2, which is really negative 1 over x squared. The exact same thing. The nice part about this is that now we can do this with other functions where we can rewrite the exponents. For instance, let's look at 1 over x to the 6. This is really x to the negative 6. And now we can do the power rule where we take this exponent, make it the coefficient, and subtract 1. So the derivative of this function is negative 6x to the negative 7. Or, if you'd rather, it's negative 6 over x to the 7. So we can do the power rule on lots of different things. I think on the chart on Canvas, I have this separated as a new line because it's going to be needed to be separated later on in the semester. But for now, we're going to really focus on the fact that this is really just the power rule. We'll see another application of that a little bit later. All right, now let's see if we can figure out how to deal with coefficients. This is the constant multiple rule. Let's say we've got some number multiplied by another function. Basically, this is going to work out the exact way that you'd like it to work out. We're going to just take that coefficient and multiply it by the derivative of that function. What I mean is this. Let's say that instead of x cubed, we have a function that's 6x cubed. What we're going to do is we're going to say this is really 6 times x cubed. And so the derivative is going to be 6 times the derivative of x cubed. I'm using this d over dx notation. Remember, this just means derivative of x cubed. Well, the derivative of x cubed, we can do the power rule on. So this is going to be 6 times 3x squared, or it's really 18x squared. Now, realistically, what we're going to do is just kind of look at this and say, all right, we'll bring our exponent out front. But now when we bring it out front, we're going to multiply and then subtract 1. So the derivative of 6x cubed is now 18x squared. We can do another one of these really quick just to make sure that we're okay. Let's say y is, I don't know, 9x to the 5. Y prime then, if we bring this exponent out front, 5 times 9 is 45, and our new exponent is 4. Because really it's 9 times 5x to the 4th. Easy enough. Coefficients work out really nicely. Coefficients just get multiplied into the derivative of the function that they're being multiplied on. Sums and differences. These work out really easily too. If you have two functions that are added and subtracted together, then the derivative is just the derivative of each piece added and subtracted together. What this really gives us the opportunity to do now is take different things, put them together into one function. We can look at things like polynomials now. We can look at things like negative 2x cubed plus 4x squared minus 9x plus 2. And what we can do now when we look at the derivative is we'll just look at each term individually. The derivative of negative 2x cubed is going to be negative 6x squared. We'll bring the 3 out front, multiply it, subtract 1 from our exponent. Similarly, we can do the power rule here again. This is going to be just 8x. This one is weird every now and then. I'm going to put a little exponent of 1 on here, and then it becomes a little bit easier. We'll bring that 1 out front. Now we have negative 9, x to the 0, so we'll just say it's negative 9. And this constant piece at the end just goes to 0. So the derivative is really negative 6x squared plus 8x minus 9. So for any combination of functions, adding and subtracting, we'll just split it up and look at each term individually. That's pretty much everything we need to know for now. So what this means is that we can go ahead and say things like y prime in this case. Maybe actually I'll give you a second. Try some of these on your own. This one and this one are a little bit weird. What I'll do is I'll give you some hints in a second. So give a shot to these three. I'll give you the answer to the first one because it's not too bad. And then I'll give you some hints onto the second and third one and let you try those. All right, if you've taken a look at this first one, the derivative here is going to be 35 x to the 6 minus 6x plus 0, but I'm going to leave that off. For this second one, I'm going to rewrite this. I'm going to say this square root, we haven't looked at that yet, but that's really just x to the half. We can use rational exponents to represent roots. Cube roots then, if we want to do this over here, we'll say the cube root of x is really x to the 1/3. Now we can do the power rule on it. Similarly, I'm going to rewrite this using a negative exponent. So now go and give this a shot. And on this third one, I want to show you that we can break this fraction up. I like looking at these and calling them upside down triangles. Anytime we have a fraction with more than one term on the top and only one term on the bottom, we can split this up and say this is really 4x cubed over x squared plus 8 over x squared. Normally, if we had fractions with common denominators like this, we'd add them up together, but we're undoing that. So this is really 4x cubed over x squared is really just 4x, and then I'll use those negative exponents again. So I'm going to switch to blue for my derivatives, but go ahead and see if you can find the derivative of this function and this function using the power rule that we have. So y prime is half x to the negative half. I'll rewrite that in a second and show you what that looks like. And here we're going to have plus 12, if we bring the negative 4 out front, x to the negative 5. Because these are negative exponents, they really belong in the denominator. So this is 1 over 2 square root x. That's really the negative, meaning it's in the denominator, half, meaning it's a square root, plus 12 over x to the 5th. So that's what this derivative is. And here we've got that y prime is going to be 4 minus 16x to the negative 3, which we can say is 4 minus 16 over x cubed. I'm not going to be really picky with whether you change these negative exponents to things in the denominator like this. So really, I'll take either one of these answers, and same thing, either one of these. But later on, it's going to be really helpful to write them using these fractions and things like that, putting things back in the denominator. So I'm going to keep writing those on our notes here just to get you used to the fact that we can rewrite them, but I'm fine with either one. That's everything that we've got. At this point, you can go ahead and just practice finding a bunch of derivative functions. We can still do the same thing with these derivatives. We can evaluate them to find slopes of tangent lines. We can then use that to find equations of tangent lines. But all of the limit stuff we don't have to worry about now if we have these power rules.